Hey everyone, welcome back. In this lesson, we're going to be building on some of the things that we did before break, as well as what we reviewed together today in class. So using our knowledge of dilations, proportions, and angle relationships. So that's maybe been a little bit longer since we've talked about those. I will define similarity. This is new to us. Identify similar figures. Right, as well as solve for missing parts. So we're going to be combining all of this. So maybe you remember, and I mean, I'm going to now reference going back all the way to the beginning of the year. We started off, talking about rigid transformations, right? And so we talked about, let's see if my pen wants to work today, rigid transformations and how those maintain their shape and size. And what happens when a figure undergoes a rigid transformation is that the preimage and the image are congruent, right? They're the exact same. And all corresponding sides are congruent and all corresponding angles are congruent, right? And so we talked a lot about that. And we did a lot of different things to kind of prove congruence, and then we actually did some formal proofs of congruence. And then we took a step back and we took a look at another type of transformation, which was dilations, and we did these on a grid, right? And so dilations, while they didn't maintain their size, they maintained their shape, right? So like just like when you go to the eye doctor and you get your eyes dilated or you're zooming in on a picture, it's keeping everything proportional, right? So something's getting bigger or smaller, expanded or contracted, enlarged or reduced by a scale factor. And so we did a lot with dilations on a grid, whether you are identifying the center and the scale factor or you are graphing given the center and scale factor. We also then took a look at proportions and ratios versus proportions and setting up two equivalent ratios in order to solve them, right? And we use that method of cross multiplication in order to successfully solve proportions. And then finally, we can go all the way back to some angle relationships that we learned about parallel lines, right? And maybe you can think about how this ties in. One of the things we talked about with dilations is that and the new segment and the old segment are always going to be parallel. We even did it with equations of lines, and we saw that the slope was the exact same. Right, so using all of this information, we're going to actually define this word similarity, right? So rigid transformations prove congruence. Non-rigid transformations, like for a dilation, specifically a dilation, is going to prove something that we call similarity, right? Like they're not exactly the same, but they're the same shape, just maybe a different side, right? And so using that definition, we're going to be able to identify if figures are similar or which figures are similar, as well as set up proportions with similar figures to solve for missing parts. So with that being said, let's get started. So we're going to start off here, and hopefully maybe you have this printed out, maybe you're writing notes on a separate sheet of paper that you can follow along with me, and maybe you want to pause the video and try this on your own. So we're going to be graphing the image of penta under a dilation with a scale factor of 1/4, and it's going to be centered at the origin. Let me try to zoom this in. Right, so we like when it's centered at the origin, when it's centered at 0, 0, so we can just multiply the points, right? So this point, and we're going to be naming it S, C, G, B, R. So I'll start with P, because that'll be S. So 1/4, so I'm going over 2 and up 8. A quarter of that, 2, 8. I'm essentially multiplying this by 1/4. It's going to be 1/2, and then 2. 1/2, 2. I don't know why this thing never wants to work for me. Goodness. Okay, and that'll be S. And there's my point. All right, and then we'll go ahead to E, and E is 10, 0. So if we multiply that by 1/4, we get 5/2. So we get 2.5, 0. So I'm going to go ahead and put a point at 2.5, and that'll be C. And then let's go to N. Down here is 6, -8. And notice I'm not doing too much explanation here because this is something that we did, right? So 6 times 1/4 is what? 1.5. And then negative 8 times 1/4 is negative 2. So 1.5, negative 2. SCG, right? So I'm just going through this. PE, I'm going in order. So I've got SCG. T is negative 2, negative 8. Let's not spend too much time on this. We did the opposite. That'll be negative 1/2, negative 2, negative 1/2, negative 2. And that's SCGB. And then R is going to correspond with A. Remember the corresponding place, even when we did congruent statements, this was true. So negative 6, 0. And we've got negative 6 times 1/4 is negative 1.5, 0. Negative 1.5. So that'll be SCG, SCGBR. And then I'll go ahead and connect to this, right? So it should just look like a reduction, a smaller version of the same thing. Oh goodness, I don't like that line. Right? And one of the things that I referenced was that like the new segment and the old segment should be parallel, right? These two are parallel. They have the same slope actually. And even just like from eyeballing it, we can tell that they're never going to intersect, right? And that's true with all of those. Okay, so everything happened proportionally. So maybe you recall filling in a table like this for congruence because we did them. So now we're going to do it with similarity because in fact, these two figures are similar. They're the same shape, but different sizes. Use the table to identify corresponding angles and corresponding sides. So corresponding angles, they're congruent. Check this out. You've got parallel lines. I don't have a transversal, but if I created a transversal, those two angles are corresponding angles. Like you could slide up the transversal, right? So I could actually extend these even, and I would be able to slide up and then slide over because everything's parallel, right? Pretty cool. So I'm just going to write it out as congruent statements here. So angle S is congruent, and I only need one letter. Why? Because there's not multiple angles that it could form. There's only one, right? You can use 3 if you would like. And then I'm going to just go, it doesn't matter what order I go in. I'm just going to go with the order that it said to me in. Angle C is congruent to, angle G is congruent to, angle, maybe you're filling it in. Angle B is congruent to angle R is congruent to angle. Those are bad congruent signs. It's okay. I've got room for improvement. Penta, right? Remember, you've got to pay attention to what it actually corresponds to. I just went with how it was written out here, right? The order matters. I could take this away and we can still fill in this table. P and S, E and C, N and G, T and B, A and R, right? If I switch these and said angle P is congruent to angle S, fine. So then here's where you want to be careful. The sides are not congruent. We know that, right? They're each going to be 1/4 of the length. So I'm going to figure, and there's a variety of ways I can do this. I want to use the scale factor in writing this out. So I'm going to start with RS. RS is 1/4 of what? Of is multiplication in math. So 1/4 of AP. Oh, right? This is 1/4 of what it's parallel to. SC is 1/4 of PE. SC equals, notice I'm not putting anything with congruent, 1/4, I forgot what I was writing, PE. I'm just going to keep going around. CG is 1/4, it's all happening proportionally, of EN. What else do we have? CGB is 1/4 of NT. And finally, so I've gone all the way around, BR is a fourth. These have the corresponding sides and the corresponding angles are separate. It's not like this angle goes with this side, okay? So I could do this in a different order. So BR is a fourth of TA, right? It's important for us to know that corresponding sides are what we call proportional. I could be writing things out like the ratio of RS to AP equals, sometimes you'll see this, the ratio of SC to PE, right? Oh, they're proportional. I can write proportions. CG over EN. What's in the fractions? These correspond, but they're not the same length, right? But that ratio is going to stay like it's all happening proportionally. It's all dilating proportionally. I'll finish these off. So then I had GB over NT equals to BR over TA, right? And with all of these things being true, my two figures are similar. And the symbol for that, I could then say, and remember the order you write this in, we control the first one, but the order matters, is similar, that's the symbol, to SCG. Ooh, no, that is not a C. BR. Okay? So the sides are not similar. Sides can't be similar. The figures are similar. What leads to figures being similar is angles being congruent, corresponding angles being congruent, and corresponding sides being proportional. That scale factor. Okay. So, knowing that, we can take a look and figure out a bunch of information about similar figures. So actually all of these up here are similar, right? So check this out. Like I can show or I can confirm here, I only know two angles. Why does the third one have to be the same? These two have to be the same. Why? My gosh, remember the triangle sum theorem? If these two are congruent and these two are congruent, they both add up to 180. These two have to be congruent. Right? So then, I could set up proportions to solve for that missing side. X over 18 equals to, right? X corresponds to 18, 15 corresponds to 20. I can pay attention to the angles that it's between. Same thing here, right? Like we can confirm, we know that corresponding angles are congruent, but I could set something up like 6 over 12, right? Pay attention to the angles that it's between, is equal to 10 over 20 is equal to 7 over 14. Well, yeah, those are all 1/2, right? So I can confirm that they're similar, right? And we could do that with all of these, actually, right? Ooh, check this out. These lines are parallel. Don't we know that these angles are congruent? And these angles are congruent? They're corresponding? And we know that this angle is congruent to itself? Whoa, we've never seen the reflexive property used for angles. Pretty neat, huh? I think so. So, what should we know about similarity? So if a polygon undergoes, so any closed figure undergoes a dilation, the image and the pre-image are what we call similar. This is a pretty neat fact. All equilateral triangles are similar. They're all dilations of each other. Well, what's an equilateral triangle? It means that all three angles are congruent, right? All three angles are 60 degrees. No matter how big or small, that fact is true. All sides, this is also, we could say, equiangular. Let's see if my pen wants to let me write it. Equiangular is that all the angles are equal. Equilateral is that all the sides are equal. Lateral. So like if this is 2, this is 2, this is 2, this is 2. If this is 5, this is 5, this is 5, this is 5. Check that. It's a scale factor, right? 5 over 2, new over old, if this is the new one. All circles are similar. Pretty cool fact too, right? The only real measurement that everything is based around for a circle is the radius. right? So that's really my main measure here, the radius. And what would happen, I mean, maybe you remember how to find circumference, pi times diameter. It's going to change the same proportion though, right? So like if this is 2 and this is 8, oh, that doesn't make sense. If this has a radius of 2 and this is a radius of 8 inches, oh, then it's going to be 2 pi and 8 pi, right? It's going to happen proportionally. Circumference is just a length. It's like perimeter. All regular hexagons are similar. What's regular mean? Regular means that all sides and angles are equal. Right? So a hexagon has 6 sides. So if it's regular, that means that this is not well drawn. That means all of these sides and all of these angles are congruent. Right? So it's kind of like a circle, right? Where all of it are, it's like an equilateral triangle, but for a hexagon. Like I can have, or an equilateral triangle is a regular triangle, actually. Right? A square is a regular quadrilateral. Which brings me to my next point. Oh, wait. Darn, I thought I put all squares are similar. All regular octagons are similar. All regular, whatever the polygon name is, are similar, is really how this is going to work anytime you have a regular figure. So that's a good vocab word for us to know and recall. So just to summarize what I've kind of said in the last few slides, if two figures are similar, corresponding sides are proportional. There's no symbol for proportional. No symbol. I'm going to write that. No symbol. I keep saying that because that's a super common misconception. That similarity symbol means similar, does not mean proportional. And similarity comes from size being proportional and corresponding angles being congruent. Right? And so we looked at this example. We looked at this example as well, right? And I was able to say that, okay, look, corresponding angles are congruent. Sometimes it helps to draw these triangles separately, right? So knowing that information, determine if these pairs of triangles are similar. And I purposely made these a little bit challenging, right? So I didn't give you a ton of information. So what I liked, I did, but I didn't give you every piece of information. What I like to do sometimes is draw the triangles separate if you're having trouble picturing them, right? So here's one of the triangles. It's this big one. The side lengths of that triangle, this is a 10, this is a 15, right? 3 is not a side length of a triangle. 2 is not a side length of a triangle. And then I have this little one, or smaller one, I don't know if I would necessarily say it's little, right in here. Right? And we can even see like what corresponds, right? So hopefully you see these lines are parallel. So we know that these angles are congruent, they correspond. These angles are congruent. And then these two triangles share this angle. So it's congruent to itself by the reflexive property, right? The reflexive property we only knew for sides. We never had overlapping angles, right? That's pretty cool, reflexive. Nothing you learn ever goes away. So I know that corresponding angles are congruent. Let's check out the sides, right? So let's see what happens when I do the purple side, 12 over 15. Is that the same thing, right? The 3 is irrelevant to me. The 2 is irrelevant to me. Is that the same thing as 8 over 10? Is that the same thing as 4 over 5? Right? So you can cross multiply, or why don't we just go ahead and simplify? This is 0.8, or 4/5 if you simplify it. This is 0.8. This is 0.8. So here we've shown that corresponding sides are proportional, corresponding angles are congruent. So therefore we could say, let's say I named it triangle FDE is similar, here's the similarity symbol, to triangle F corresponds with H, D corresponds with D, that's the one that it shares, and then E corresponds with G. Okay. Hopefully you're seeing some similarities. Okay. Good joke. Okay, so this next one here, we've got some sides labeled here. And then we also have these sides, these lines or segments as being parallel. So if you picture this as the transversal and these as your two lines, oh, these two angles are congruent. They're alternate interior. Alternate interior angles are congruent as long as those lines are parallel. Well, I could do the same thing if I said this was my transversal, right? This angle is congruent to this angle. Alternate interior angles. I'm just going to go out on a limb and say these two. How would I know that? Remember vertical angles? Remember on the objective I talked about special angle relationships? See how they come up? And then we'll go ahead and let's check that the sides are all proportional, corresponding sides. Well, this is a little tricky because there was clearly some rotations that happened. So what I like to do is figure out which is my shortest side. Let's look at this triangle over here, ABC. My smallest number on ABC is 2. What's my smallest number on this other triangle, ALK? 4.5. So that's what it would have to correspond to if they are similar. I mean, regardless, but. Okay, so is that the same thing as, let's go with the next one, 3.6 and 8.1. 3.6 and 8.1. Is that the same thing as the third side, 4/9? So it goes in order from smallest to largest. That's my favorite preferred way of doing it. So then we can just go into our calculators or however you really want to do this. This is 4/9. It's 0.4 repeating. I'm going to write it as 4/9. 3.6 over 8.1 is also 0.4 repeating, which is also 4/9. And then, oh, look at that, 4/9. Right? So therefore, these two are similar because you have corresponding angles are congruent, your special angle relationships, and then we have corresponding sides are proportional, and we showed that. That's what this down here said. So I could go ahead and say triangle, let's say I said BAC is similar to, what does B correspond to? A. A corresponds to A, and then C corresponds to L. And that's why marking off the triangles are so important because it makes this step simpler. You control the first one, unless we control it. And the second one follows. Right, so like proving that things are similar. So let's stretch this a little bit further. Let's kind of take a little bit more into this. So the two triangles above are similar. If the scale factor is 2/3, so I know that it's getting smaller. I know that it's a reduction. And AB is 14. I'm trying to find DE. I'll call it X. Creative. Right? So 2/3. So if I did new over old, X over 14. 2/3, I know it's getting smaller. I know this one has to be my new one. I know this has to be my old one based off of this scale factor. Well, let's figure it out. If it's 2/3, oh, you get a proportion. You can go ahead and cross multiply. And I've got 3x equals 28. You can go ahead and divide by 3. Right? That, if it doesn't simplify, you can always leave it like that. I think it's preferable actually to leave it like that. It's 9.3 repeating, or 9 1/3, but we don't like to round decimals, or we like to avoid that for now. So 28/3 is perfect. Okay, I had to make this connection. I have to show you guys this. So we've got this triangle, and given DE is the mid segment, so you got to really pull in some background knowledge here, guys. If it's the mid segment of ABC, we're going to try to prove that they're similar. So what do we know about mid segments? We know that this mid segment is parallel to this. We also know that this segment is congruent to this segment. This segment is congruent to this segment. Right? If those two are parallel, we know that this angle and this angle are congruent. We know that this angle and this angle are congruent. We know that this angle is congruent to itself. So I know that corresponding angles are congruent. Right? I've got A BC, and ADE. So check this out. I'm going to put numbers on it just to like kind of talk about it. Or you know what? Yeah, right? So if this was 2, this whole length is 4. If this was 3, this whole length is 6. If this was 4, what's the base? Remember it was half? This is half, so this is double. So like, check out this scale factor, right? I've got, 2 over 4. I've got 4 over 8. I've got 3 over 6. Oh, I've got a scale factor of 1/2. If I picked any number, that would be true. It's just a dilation. And in fact, you know, the center of dilation is just point A, right? Everything's getting closer to it. Or it's getting twice as far away. You guys did this on a grid, right? So if we have a triangle and we've got the mid segment, we actually know that the 2 triangles that are created are similar. Neat, right? So the mid segment's parallel to the third side. How could this proof, or how could you extend this? Send the proof to prove this property. We used this, but if we knew, if I just told you basically that the triangles were similar, you could use the converse of the corresponding angle theorem to figure it out, right? If corresponding angles are congruent, then the lines have to be parallel. The mid segment is half the length of the third side, right? It's all happening proportionally. So we're gonna finish up here. We're almost done. This is our last one. So I know there's a lot going on here, but you got a lot that you can practice with. So use what you know about similarity to determine which 2 triangles are similar. Okay, so like let's set up proportions. I'm gonna actually just name them 1, 2, 3. This would be a really good place if you are like, I think I know what she wants me to do. Pause the video. So I'm gonna start with triangle 1 and 2. It's an ugly 2. Oh, I think I made it prettier. Okay, and I'm going to do the exact same thing I did on the other slide. So let's go ahead and set up some proportions. 4.2 over, that's the smallest 9. If it's similar to triangle 2, what's smallest one is 6.3. Is that, and these are all questions. Let's go to the next one. 5.6, next biggest number is 8.4. So 5.6 over 8.4. Is that equal to this last side, the biggest one? 6.3 over 9.45. So then I'm actually just going to pick up my calculator, no point. 4.2 over 6.3 is 2/3. It's 0.6 repeating. 5.6 over 8.4 is also 0.6 repeating, which is 2/3. And then finally, 6.3 over 9.45 is also 0.6 repeating, which is 2/3. So I actually have already figured it out. I know, oh no, oh boy. Triangle ABC is similar to triangle, and pay attention. So A is between, and this is why I like to highlight it. Oops, I never highlighted it. This, oh, what color is this? Like, it's like a dark turquoise. And this lime green, so dark turquoise and lime green, so it corresponds to F. And then B is between that red, that burgundy, and green, burgundy, so D, and then E, right? And I mean, realistically, I kind of wish I hadn't gotten it on my first try, but if I was going to try 2 and 3, I would do the same thing, right? So my shortest side over here is 2.8. 2.8 over 6.3. I'll just show you what happens. Is that the same thing as, what's my next side? The next biggest one is 2.52. 2.52. And I want to just emphasize it's okay if you flip these fractions as long as you're consistent. The same triangle should all line up in the top. So 2.52 over 8.4 and then 3.15 over 9.45. Then I can simplify them. So 2.8 over 6.3. I get 0.4 repeating, which is 4/9. 2.52 over 8.4. I get 0.3, which is 3/10. Oh, those aren't the same. So I don't even need to keep going. These two aren't similar. Corresponding sides are not proportional, right? And the same thing would happen if you did 1 and 3. Okay? So we did a lot in this lesson, but we tied in what we know about dilations and proportions, as well as what we are, like, the background knowledge that we have from a lot of this school year about angle relationships to actually define similarity, right? So that meant that two figures are similar if corresponding angles are congruent and corresponding sides are proportional, and there is no symbol for proportional. We identified some similar figures, and we talked a little bit about solving for missing parts. So what I would strongly encourage you all to do now is you have part 1 of your homework assignment, that Go Formative, is to start working on that so that you can get feedback from your teacher and know what questions you might have to get some help and support with it. So thanks everyone for watching, and we will see you guys soon.